Good evening, everyone, and thank you for joining me tonight. My name is Mark Gillette, and tonight's presentation is entitled Galaxy Quest. For those who know me, welcome back. I'm glad to see you here. For those who don't, let me tell you a little bit about who I am. I'm a native of Central Florida, live not far from the Walt Disney World Resort. I'm a full-time professor at Valencia College. I'm a sociology professor. I have lots of hobbies and things that I love and enjoy to do. Among them include travel and anything related to space. As such, I was selected in 2019 by NASA and JPL to be a solar system ambassador. And basically, that's a fancy way of saying that I am a public outreach volunteer to talk about all things related to NASA. Now, because of the COVID-19 situation we have going on, over the last several months, I've been doing live YouTube events, including a variety of topics, from stars to planets, and tonight the focus will be galaxies. So what I'd like you to do, if you could, is I'd like you to get involved. On any device that you're watching this presentation on, there is a chat box that's available. So feel free to, at any time, if you have any questions that I hopefully can answer for you, put those in the chat box. Now, I have an assistant here tonight. Much like last time, I discovered that it's very difficult to do presentations and monitor the chat at the same time. So I've asked my husband, Spencer, to monitor the chat box. So he's going to say hello.
Hi, everybody.
So I appreciate him working with me and taking that burden off of my shoulders so that I can focus more on my presentation and less on going back and forth from the presentation to looking at the chat box. So again, any questions, anything that you'd like to share, put it in the chat box, and as they come up, he will alert me, and I will do what I can to answer any question that you have. Now, my specialty is in sociology. That's what my master's degree is in, and I have a doctorate in educational leadership. So please notice that I did not say that I have a degree in physics or anything related to space. So you might wonder, so why is this guy doing a presentation about galaxies? It's simply because I love it. It's a passion of mine. It's fascinating to me to study and research and talk about anything related to space. So I appreciate you being here tonight. One thing I do ask of you, if it would be possible, that in the chat box, if you could please tell me how you heard about tonight's presentation, I would highly appreciate it. I'd also like to take a moment to recognize some of the libraries all over the U.S. that might be participating in tonight's presentation. And so my assistant is going to call those libraries out in recognition of their participation.
And the first one who came online to say hello was Solano Public Library, Solano County Library, and then Winfield Library. Hello. And we're expecting S.W. Smith Memorial Public Library from Pennsylvania, Bangor Public Library from Pennsylvania, Cooper C. Community Library out of Pennsylvania, Gates Public Library out of Rochester, New York, Prairie Trails Public Library out of Illinois, Prince George's County Memorial Library System out of Maryland. We're also expecting Lake Dallas Public Library out of Texas, the Wilbanks Public Library out of Oregon, Technology Equipment Center from Rutherford County out of Murfreesboro, Tennessee should be on tonight as well, Cudahy Family Library out of Wisconsin, Moore's Memorial Library out of Pennsylvania, and there are already people deciding on saying hello. Yes, so Cudahy Library is online. Hello, and welcome to the presentation tonight.
All right, so thank you so much. I'm going to go ahead and adjust my screen so that I can maximize the presentation and minimize myself, because tonight the focus is not me, the focus is galaxies. So I'm going to put myself down here in the corner and we're going to go ahead and get started. Let's take a look at the agenda, and tonight's agenda is starting with a definition. What is a galaxy? We will then turn our attention to looking at different types of galaxies: spiral, elliptical, irregular, and lunicular. We will talk about what's called the Hubble sequence, named after Hubble, the famous Edwin Hubble. We will then take a quick look at galaxy clusters and superclusters, and then whatever remaining time we can have Q&A. I will be showing you a number of pictures tonight, and on the right-hand side of your screen, you see a picture that I've taken of M104. The M stands for Messier. He was a gentleman that lived a long time ago that started classifying all kinds of DSOs, or deep space objects, including galaxies. M104 is also often called the Sombrero Galaxy, and you can see by looking at the picture why it's called that. The Sombrero Galaxy is roughly about 31 million light years from Earth. Now, in one of my earlier presentations this year, I talked about light years, so as a quick reminder, a light year is the amount of distance that light travels in 1 year. So what you're looking at here on the screen, this galaxy, it took about 31 million years for the light to leave that galaxy and to enter my telescope. Okay, pretty amazing. All right, let's take a look at a definition here. Galaxy. A galaxy is a large group of stars, gas, and dust bound together by gravity. Galaxies are classified by shape. As I mentioned in the agenda, there are 4 types: elliptical, spiral, irregular, and lunicular. It is believed that galaxies form when small-scale structures gradually merge to create larger structures. Computer simulations suggest that in the early life of the universe, cold, dark matter started to clump together in localized regions. These clumps acted as seeds, attracting yet more matter and eventually developing into what's called proto-galaxies, and then eventually mature galaxies. This happened in numerous localized regions throughout the universe, leading to the distributions of galaxies seen today. Relative to their size, galaxies are quite closely packed together and live in clusters. Much like we human beings live with other people. We generally don't live alone, but we can. The Milky Way galaxy, our home galaxy, which is a barred spiral galaxy, is part of a cluster of galaxies called the Local Group, which contains 45 other galaxies. Clusters of galaxies are held together by gravity, and it is that same force that in turn links clusters of galaxies together to form what we call superclusters. Now, the Local Group, which we are a part of, is a part of the Virgo supercluster. Okay, anything going on in the chat? Again, keep in mind that you can put those questions in there anytime you'd like so we can make this interactive. Everything looking good? All right. Galaxies range in size from dwarf galaxies like the Large and Small Magellanic Clouds, and I'll talk a little bit about those later and show you actually a picture of them, with a few 100 million stars, to giants with up to 1 trillion stars in the galaxy itself. There are an estimated 2 trillion galaxies in our known universe. Only a few galaxies have been assigned names, such as the Andromeda, Whirlpool, and the one I was showing you earlier, Sombrero. Most are classified by catalogs, such as Messier, and that brings us back to when I was talking about the number system that was used for the Sombrero. The New General Catalog, NGC, and also the Index Catalog, or simply IC. Now, the picture that you're looking at on your screen is called the Hubble Ultra Deep Field Image. And this picture comes from the Hubble Space Telescope, which is about 250 to 300 miles orbiting the Earth, above the Earth. And quite a number of years ago, NASA decided that it would pick what they thought was an obscure section of the sky. There was nothing special about it. And they had the Hubble Space Telescope take a number of images of this section of the sky. I believe it was over 2 or 3 days. And they merged and stacked them all together. You have to do that in order to bring out the light, to collect the light from the imaging process. And here's what Hubble shows us. In a very obscure section of the sky, there are roughly 10,000 galaxies. Okay, and again, this makes up a very, very small segment of the sky. So if there are approximately 10,000 galaxies in this obscure section of the sky, then we can safely assume that there are many, many, many other galaxies throughout the known universe. I highly recommend that when you get the time, you go on to nasa.gov, because Hubble, the Hubble Space Telescope, took quite a number of pictures of different types of galaxies, and you can see some of them on your screen right now. And they are classified according to the Messier catalog. So lots of neat things on nasa.gov. If you've not checked out their website, please make sure that you do so. All right, so now let's take a look at the characteristics of the 4 major types of galaxies. Spiral galaxies have spiral arms in a relatively flat disk and a central bulge. The bulge has a large concentration of stars. The bulge and halo consist mainly of older stars, where spiral arms have more gas, dust, and therefore younger stars. Some spiral galaxies are called barred spirals. As I mentioned earlier, the Milky Way, our home galaxy, is a barred spiral galaxy because the central bulge looks elongated, like a bar. In barred spirals, the spiral arms of the galaxy appear to spin out of the ends of the bar. Spiral galaxies rotate slowly. Well, in our perception, they rotate slowly. Typically once every few 100 million years. In other words, it takes a few 100 million years for this here to completely spin around one time. Spiral galaxies do not behave like solid objects. Stars orbiting farther away take longer to complete an orbit than those close to the core. That's a look at spiral galaxies. Now let's take a look at elliptical and irregular galaxies. Elliptical galaxies are round or oval with stars distributed fairly uniformly throughout. They have a bulge or halo like spiral galaxies, but don't have the flat disk of stars. Almost all the stars in elliptical galaxies are middle-aged or older. It is rare to find any sign of star-forming gas and dust, hence star formation has long since ended. Irregular galaxies have no identifiable shape or structure. Scientists believe that at least some of the irregular galaxies are a result of interactions with other galaxies. And I'm going to be showing you interacting galaxies in a few minutes. These galaxies typically contain a lot of gas, dust, and hot blue stars. Two examples of irregular galaxies would be the Large and Small Magellanic Clouds. Lunicular. Lunicular galaxies appear to be relatives to ellipticals, which are dominated by a roughly spherical nucleus of old red and yellow stars. However, around this nucleus, these galaxies also have a disk of stars and gas. This links them to spiral galaxies, although the nucleus is often considerably bigger than it would be in a spiral of similar size. The overall shape is often described as that of a lens, hence the name lunicular galaxies. Edwin Hubble came up with a way of classifying galaxies. So I'd like to show you this short video on Edwin Hubble's classification system.
In 1926, there were enough galaxies known for Edwin Hubble to create a morphological classification scheme. This is his diagram. His students called it the Hubble tuning fork. Hubble's scheme divides galaxies into three broad classes based on their visual appearance. Elliptical galaxies have smooth, featureless light distributions and appear as ellipses in images, like Centaurus A. They are denoted by the letter E, followed by the integer n, representing the degree of ellipticity. Spiral galaxies consist of a flattened disk with stars forming a spiral structure and a central concentration of stars known as the bulge, like the Whirlpool galaxy. They are given the symbol S, or SB, if it has a bar core, followed by a letter A through C. As we move from A to C, the spiral arm structure becomes more open, the amount of dust in young stars decreases, and the central bulge of the galaxy decreases in size relative to the disk size. Lenticular galaxies also consist of a bright central bulge surrounded by an extended disk-like structure, but unlike spiral galaxies, the disks of lenticular galaxies have no visible spiral structure and are not actively forming stars in any significant quantity. NGC 2787 is an example of these. They are designated S0. These broad classes can be extended to enable finer distinctions of appearance and to encompass other types of galaxies, such as irregular galaxies, which have no obvious regular structure, either disk-like or ellipsoidal. The Large Magellanic Cloud is an example of this. Since Hubble, others have added characteristics such as bars, rings, and spiral arm characteristics.
Okay, and so that is a short presentation or video on Edwin Hubble's classification scheme, also known as the Hubble tuning fork diagram, which is the most commonly used system for classifying galaxies. Now, as I mentioned earlier, galaxies tend to cluster around other galaxies. So here I have a short video on galaxy clusters and superclusters.
Somewhere in the universe is a small blue planet, the third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense center. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black and a neighboring structure, Perseus Pisces, in red. Scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighboring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
Okay, I hope that you enjoyed that. It's pretty neat stuff. What I'd like to do now is show you some images that I have been able to capture of different galaxies. These images come from the last 3 years. I do want to warn you that they are not NASA quality per se, because I don't have a multi-billion-dollar telescope up in space that I can take pictures with. But I'm very proud of these because these are pictures that I have taken myself. I do want to give credit where credit is due. I have a friend, his name is Leonard, who helped me extensively select a telescope and helped me learn all about astrophotography, helped me what's called post-process some of my images. And so he has really helped me a lot, and I do want to give him credit for getting me to where I am now. So let's start with Messier 106. It is a spiral galaxy on the left-hand side of your screen. It was discovered in 1781 by a gentleman by the name of Pierre Méchain. It has a supermassive black hole a Type 2 supernova was observed in M106 in the year 2014. And for those who may not know, a supernova is when a star is at the end of its life, a very large star is at the end of its life, and it explodes. M106 is roughly about 22 to 25 million light years from Earth. So again, keep in mind that this light that eventually ended up on this image took somewhere between 22 to 25 million years to get here. So it's really, really far away. It's not 22 to 25 million miles from here. It's 22 to 25 million light years from here. In essence, that means that it is trillions and trillions and trillions and trillions and trillions of miles away from our very small little blue planet Earth. Over here, you can see that I captured another galaxy. This is NGC 2217. It's approximately 60 million light years from Earth. You might wonder, what are these green, blue, and red lines throughout my picture? Well, since I'm still in the process of really learning about what's called post-processing pictures, something did not go well in my post-processing, and so there you go. But I'm still proud of what I have there. All right, on the right-hand side of your screen, you have what's called Messier 104, also called the Sombrero Galaxy. It is a lunicular galaxy. It is roughly 31 million light years from Earth. And you can see that it is what's called an edge-on galaxy because we are looking at it edge-on. Unlike this one, 106, you can kind of see it. It's probably at about, what, a 45-degree angle. Here we're looking at this galaxy edge-on from our perspective on Earth. Okay, M104 is about 30% the size of our Milky Way galaxy. It has a prominent dust lane, and you can see that prominent dust lane right there. Okay, lots of dust and gas. All right, let's go on and take a look at some more. Now you're looking at the same galaxy here. On the left-hand side of your screen, you can basically see one picture that I took, and it's not what's called post-process. So I believe this is one 30-second image. On the right-hand side of your screen, you can see multiple images that have been stacked together and has been post-processed, so it looks a bit more realistic. Same thing, NGC 4565, also called the Needle Spiral Galaxy. This is about 30 to 50 million light years from Earth.
And you're just using a regular telescope?
And yeah, I'm just using my regular telescope, which is a Scientific Explorer. That's the brand name. And I have a Canon camera. And what I do is I take out the eyepiece. I put in the camera. My camera is connected to my laptop. And I have software that I can tell the camera how often to take pictures, how many to take, how long the duration should be. And then once I collect, depending on what I'm trying to do and how good I want the quality to be, as few as maybe 20 or 30 images all the way up to 200 and 250, I use other software to do what's called post-processing, to merge and stack those pictures all together because it's all about collecting light. And then I use other software, PixInsight, if you're familiar with post-processing, to do the finishing touches to make it look like what it should look like.
You have to tell them it has to be very dark tonight.
It has to be dark. There are a number of challenges when it comes to astrophotography. It can be very, very challenging. There is a steep learning curve I have found in order to photograph to do astrophotography. So you really have to have a lot of patience, but it can be very rewarding if this is something that you're really into. And so when I look at my photos, again, they're not NASA quality, but I get really excited about this because these are pictures that I've taken, and so I'm very proud of them. All right, let's look at a couple others here on this screen. On the left-hand side, we have Messier, or M51, also called the Whirlpool Galaxy, which is a spiral galaxy. This is about 23 million light years from Earth. So all of these galaxies we're talking about are incredibly far away, which to me is just amazing that, you know, we have the technology today. We have telescopes and cameras that we can take pictures and that we can share with one another, because people a couple hundred years ago didn't have any of this technology available to them. And they didn't even know that this stuff existed in the sky. They actually believed that, you know, the Earth was the center of the universe, and there were a couple things that they thought maybe were planets and the sun and maybe some stars, but very limited. But today we have really cool technology, and we can see and image so many of these things. All right, so as I mentioned earlier, I would talk about an interacting galaxy. And here you go. The Whirlpool Galaxy is interacting with this other galaxy right here. And generally when these galaxies are interacting with one another, what they tend to do is they tend to kind of go back and forth, and then they merge into a larger galaxy. You would think that in the process of these galaxies interacting with one another, that there would be a lot of collisions. But generally there aren't very many collisions at all. Why? Because things are so separated by large and large amounts of space that they don't actually collide with one another. And that's pretty neat. All right, so this is an interacting galaxy. Now, I didn't mean to do this when I photographed the Whirlpool Galaxy, but one of my astronomy friends, when he saw this picture, he said, "Hey, Mark, did you know that you captured another galaxy?" And I'm like, "No, I didn't." And so he pointed it out to me, and right here, you can see IC 4263. It's a barred spiral galaxy. It's edge on, so we're seeing the edge. We're not seeing it face on like what we're seeing here. This galaxy right here is roughly 125 million light years from Earth. That's really, really far. All right, on the right-hand side of your screen, you see M101, which is also called the Pinwheel Galaxy. It's a spiral galaxy. It's roughly 21 million light years from Earth. It was discovered by Pierre Méchain in 1781. The diameter of this galaxy is about 170,000 light years. That's compared to our Milky Way galaxy at roughly about 100,000 light years across. It has twice the number of stars as our Milky Way, at around 1 trillion stars. So there are roughly 1 trillion stars right here that make up this one galaxy. By the way, when you see pictures of galaxies like this, and you see these other stars here in the background, those would be stars within our own Milky Way. So you're imaging a part of the sky. Certainly part of our sky, part of our Milky Way will be in the picture as you are looking deep into space. Okay. All right. Got a couple more for you here on the left-hand side of the screen. We have M, or Messier 63, the Sunflower Galaxy. It's a spiral galaxy. It's roughly about 27 million light years from Earth. And on the right-hand side, this is probably the one I'm most proud of when it comes to the galaxies that I've taken. On the left-hand side, the spiral galaxy that you see right here is M81, Bode's Spiral Galaxy. And over here, so this is face on, we're seeing it face on. And on the right-hand side, you have M82, the Cigar Galaxy, which is an elliptical galaxy. And we're seeing it edge on, not face on, but edge on. Both.
Someone asked a question.
Yep, okay.
So the question is, and it's from Stormy Sky Rail Productions, how old is our galaxy, and how will our galaxy react at the end of its life cycle?
So the Milky Way galaxy, I believe, the universe is about 13.5 to 14 billion years old. And our Milky Way galaxy, if I'm not mistaken, is, you're not going to quote me on this, however, is, I believe, like 10 to 11 billion years old. So it's not a newbie by any stretch of the imagination. The Milky Way has been around for a while, but there are galaxies that are older. And the second part of that question is the life as they die.
And how will our galaxy react at the end of its life cycle?
So interestingly enough,
Is this when you talk about Andromeda?
yeah, there's going to be another big event that occurs before we come to the end of the life of the Milky Way. So let me hold on that for one moment because I'm going to talk about that in just one moment. Both Bode's and the Cigar Galaxy are roughly about 12 million light years from Earth. All right, so let me start with the one on the right-hand side first. This is M33, Messier 33, called the Triangulum Galaxy. It's a spiral galaxy. It's about 2.7 million light years from Earth. Now, think about the distance I have talked about for most of the other galaxies. 20, 25, 125 million light years. This one's only 2.7 million light years. So it's really, in our perspective, certainly very, very far. But in astronomical terms, it's very, very close. And you can see that from our perspective on Earth, we see it face on. Okay? And so this is one of the larger galaxies within our local group, in which the Milky Way is a part of. All right. On the left-hand side of the screen, you see perhaps the most famous, other than the Milky Way galaxy, and that is M31, Messier 31, which is also called the Andromeda Galaxy. It is a barred spiral galaxy at only 2.5 million light years from Earth. This is our closest big neighbor to the Milky Way galaxy. And so, it is expected that in around 4.5 billion years, the Andromeda Galaxy will collide with our own Milky Way galaxy. Now, as I was talking about earlier, we would probably quickly assume that the two galaxies coming together, Milky Way and Andromeda, would create a huge collision of stars and planets and just complete disaster. But because things are so separated by huge amounts of space in our galaxy and Andromeda, and in most cases, most galaxies, scientists actually expect very few collisions of stars and planets, all things considered. Okay? So we don't need to worry about this because this is quite a number of years off, as I said earlier, about 4.5 billion years. Don't stay up tonight waiting for this big event to occur. I do have a quick little video I would like to show you about the Andromeda Galaxy. So let's take a look at this.
Hi, I'm Stefan Imler, a research scientist working with NASA's Swift satellite at Goddard Space Flight Center in Greenbelt, Maryland. This is M31, the nearest large spiral galaxy to our own. It's about 2.5 million light years away and more than 220,000 light years across. This is how we're used to seeing it, in the visible light captured by ground-based telescopes. But visible light never tells the whole story. So between May and July 2008, Swift's ultraviolet optical telescope captured 330 images of M31 and 3 ultraviolet wavelengths. The total exposure time, 24 hours. We combine these images into this mosaic. It's the most detailed view of M31 in the ultraviolet to date. The first thing you notice is the striking difference between the galaxy's central bulge and its spiral arms. The bulge is smoother and redder because it's full of older and cooler stars. Very few new stars form here, because most of the materials needed to make them have been depleted. In contrast, M31's spiral arms sparkle with dense clusters of hot, young blue stars. As in our own galaxy, the disk and spiral arms contain most of the gas and dust needed to produce new generations of stars. M31's clusters are especially plentiful in a giant ring around the galaxy. It's about 150,000 light years across. This ring of fire exists because of tidal interactions with small satellite galaxies. Speaking of which, this is M32, one of many dwarf galaxies orbiting M31. These galaxies are usually not very bright in the ultraviolet because they lack young stars. But M32's core is so bright in the UV because it likely contains many blue and old stars. The Swift mosaic reveals some 20,000 UV sources. It's important to study star formation processes in nearby galaxies so we can understand what we're seeing in distant galaxies. This rich portrait in 3 different ultraviolet wavelengths allows us to study how M31 stars live and die with much greater detail than previously possible.
Okay.
What galaxy is the Star Wars galaxy?
Oh, folks, I'm afraid to say I don't know that. I don't know that. Sorry. Perhaps my assistant might know.
It's fictional.
It's fictional. It's fictional. Last image I'd like to show you that I've taken with my telescope. This particular image has multiple galaxies. Here's one. Here's one. Here's one. And there's one. All right. I mentioned the large and small Magellanic Clouds earlier. This is a picture of me taken in Chile, the country of Chile in South America. In the northern part of the country, they have a desert called the Atacama Desert. It has some of the driest conditions in the world. It also has very, very little light pollution. And so this is an image that someone took of me. It looks, to me, it looks like a blue screen. And I'm just standing in front of a blue screen with something behind me. But this is an actual, real image. And you can see the Milky Way right here behind me. And you can see the large and small Magellanic Clouds. Those are basically dwarf galaxies of our galaxy, the Milky Way. The large Magellanic Cloud is about 163,000 light years away, and the small is about 199,000 light years from Earth. Got one more, my final video I'd like to show you about these 2 dwarf galaxies.
I'm Stefan Immler, an astrophysicist at NASA's Goddard Space Flight Center. I'd like to take you on a tour of 2 nearby galaxies in our cosmic neighborhood, the large and small Magellanic Clouds, as captured in ultraviolet light by NASA's Swift satellite. These images are the highest resolution wide field surveys of the galaxies at ultraviolet wavelength. Both of these galaxies are less than 200,000 light years away, and each contains a few 100 million stars like our Sun. If you live or travel to the southern hemisphere, you see both of these galaxies as faint cloudy patches in the night sky. Both galaxies orbit our own as well as each other. Of the two, the LMC is physically larger and nearer to us than the SMC. Their messy shapes are a product of gravitational interactions between them, tidal forces from the much bigger Milky Way, and internal processes like star formation. In visible light, we see a mix of sun-like stars, along with pink patches that mark star formation regions, where hydrogen gas is set aglow by the light of young stars. These are especially prominent in the LMC. Viewed at higher energies in the UV, the LMC looks very different. This wavelength blocks out the older stars, mostly showing those less than 500 million years old. These galaxies are relatively small, but they're also very close to us. This means they appear much larger than the field of view of Swift's telescope, so we had to take many different observations and stitch them together. Swift had to image 172 separate fields in 2,200 short snapshots to take in the whole galaxy. The LMC's most striking feature is the dramatic Tarantula Nebula. This is the most active star factory in any of the dozens of galaxies in the local group, which includes the Milky Way and Andromeda. Thousands of stars form each year within cool, dark molecular clouds. Once they start shining, they blow off their birth cloud with powerful outflows called stellar winds. These winds, in turn, sculpt the gases into the Tarantula Nebula's spider-like shape. One star here, named R136A1, is one of the most massive known, weighing more than 260 times the Sun. The LMC holds more than 1,000 star clusters formed during previous rounds of star formation. We mostly see hot, young, luminous stars, plus a few stars in exotic stages as they near stellar death. Wherever there are hot, young, and massive stars, there are also supernovae. In 1987, the closest stellar explosion in more than 400 years occurred in the outskirts of the Tarantula Nebula. Even 26 years later, the afterglow of the explosion remains detectable in the ultraviolet. All told, the new Swift mosaics reveal about 1 million objects in the LMC and about 250,000 objects in the smaller, less massive, and more distant SMC. For this mosaic of the SMC, Swift imaged about 50 fields and took 656 snapshots. One interesting feature is the massive young star cluster NGC 346. It contains the SMC's brightest star, HD 5980, a triple star system where all members are among the most luminous stars known. The intense light and strong outflows from these stars mold the surrounding gas into a shape resembling a cobweb. The Swift UV mosaics allow us to study the evolution of young stars in the LMC and SMC all in one view. That's impossible for us to do for our own galaxy because we're inside it. The images give us a panoramic window into how stars are born, evolve, and die across two complete galaxies. That gives us fresh insight into the many ways stars transform the universe into what we see around us today.
I see a question about the dwarf galaxies. What makes them dwarfs? Simply, they're extremely small as compared to the other galaxies that we have talked about, and they have very, very few stars in relation, in comparison to regular normal-sized galaxies. So it's really about the size. All right. If you are not a subscriber to my YouTube channel, I kindly ask that you consider subscribing. If you enjoyed what you heard tonight, please remember to turn on notifications or alerts so that you are aware of other upcoming events that I will be offering. I generally will post a short video every 3 months talking about what programs I have coming up in the next several months. Speaking of that, my last presentation for the year 2020 will be on Sunday, December 20th, starting at 8 o'clock p.m. Eastern Time. It's entitled 321 Liftoff. I'll be talking about rockets. So please mark your calendar for Sunday, December 20th, and I'd love to see you back. That's 8 p.m. Eastern Time, so adjust your time accordingly for those in other time zones.
Do you have time for one more question?
Yes, so now we are to the Q&A portion. So we have a few minutes, so it can be related to what we've talked about tonight, galaxies or anything else, and I will do the best I can to answer the questions, and if I can't, I'll simply tell you I can't. So put those questions in the chat box and Spencer will read them out to me.
So you have a question from Alondra Alexander. How does one become a solar system ambassador for NASA?
All right, very good. So in the month of September every year, the Jet Propulsion Laboratory based in Pasadena, California, who runs this Solar System Ambassador program, will accept applications. So it was just a couple months ago. So if you're interested in the program, I encourage you to go online, look up NASA Solar System Ambassador. You can find quite a bit of information about the program. Put together the application. Once it's posted in early September, you will need to put several references down. You will need to have some experience working with the public. And most importantly, you're just going to need to be very, very enthusiastic about anything related to astronomy, space, and NASA. And it generally takes them a couple months to process all the applications that they get. And if you are selected, you will receive a letter generally sometime in the month of December. And then it's a yearly, for the first year, it's a year term that you serve. And if you want to continue serving, it becomes a 2-year cycle from that point forward. So it's really about being very enthusiastic.
Does every galaxy have a black hole?
No, every galaxy does not have a black hole. Many galaxies do have black holes. Okay?
So one question is about within our solar system, within the Milky Way, how will our sun react at the end of its life cycle? That's a question from Stormy Sky Rail Productions.
Okay, so the end of our sun is roughly about 4.5 billion years old. The lifespan is roughly 10 billion years, so we're about halfway through its life. It is expected that as it approaches the end of its life, it will start to expand and grow. It will grow to the point of where the Earth is in orbit. The sun can come all the way to where the Earth is. This will not end very well for the Earth, unfortunately. So it's going to become a red giant. Once it gets to that stage and it starts to completely use up all of its fuel, then it will start to shrink down and become roughly about the size of the Earth and become what's called a white dwarf. From that point, it will still have some capability of producing energy, but very, very limited energy. And over a period of billions and billions of years, eventually it will run out of energy and it will go dark and our sun will die. As is the case with any living thing, there's always a cycle that it will go through. And that's the cycle for our star, the sun. It's got about 4.5 billion years left. Will grow into a supergiant, will grow very large. It will take out Mercury, Venus, probably Earth, maybe Mars, and then it will shrink down, become a white dwarf, and eventually fade out. All right. Does anyone else have any questions, anything you'd like to talk about? I'd like to give you a heads up on where I think I might be going for my what I call winter series. The Mars Perseverance rover, once called Mars 2020, is scheduled to land on Mars February the 18th, 2021. So I was thinking for my January 2021 presentation, I'd like to maybe do something and provide you some information about the Mars Perseverance rover. A lot of really cool things that they've incorporated in the suite of tools. One of them being a miniature helicopter that is expected to fly on Mars. It will be the first time a helicopter flies on another body other than Earth. So I was thinking maybe that for January, and then February, since the landing is on February the 18th, I'm thinking maybe I might put something together that might be live for the landing. I don't know if that would be of interest of any of you. If you think that either of those would be interesting, if you could put that in the chat box, then that would certainly be words of encouragement to me to get you excited about Mars 2020, the Perseverance rover. Headed to Mars right now. It was launched in late July. I think it was July the 30th. So right now it's speeding towards the planet Mars. All right. Any other questions? Mars presentation would be fascinating. Rachel Lastrom. I think I know her. Huh. The name sounds familiar, so I'll have to give that some thought.
You want to remind everybody there's a Liftoff tonight from space?
That's right. SpaceX has a launch in 1 hour, 9:56 p.m. Eastern time. So if any of you live in Florida, you can walk out your door if it's cleared up. It was cloudy earlier, and see a SpaceX launch. If not, you can go to SpaceX.com or go to NASA.com. They might be covering it, NASA.gov. But there's a launch in about an hour.
So one more question. How will the gravity on Mars affect the operation of the helicopter that's going to be operated on Mars?
So they have accounted for the gravity on Mars. Don't quote me on this, but I think it's roughly about 30%. 30% of what we have here on Earth. Don't quote me. It's significantly less. So the engineers accounted for the reduced amount of gravity. And so hopefully it was engineered to be able to take flight. And it's not going to go 200 miles. They only expect it to go roughly, I think, about roughly 15 feet off the ground. Probably not, only going to go, so many hundreds of feet. But if things work out with that helicopter, the name is Ingenuity, then that will set the stage for including other helicopters on other future missions to Mars and perhaps other planets. So, all right, we are about at the top of the hour, so I thank you so very much for joining me tonight. I hope that you enjoyed it. I hope that you learned something. Thank you to my husband Spencer for helping me out here. Thanksgiving is just a few days away, so let's be thankful for all that we have, because we truly are very fortunate. Though we live in difficult times, we all have things that we are fortunate for. So thank you so much for joining me tonight, and I hope to see you back for my presentation in December. Good evening.